All right, so we're back again, and we're going to very quickly review the concepts from the previous video, which dealt with additive color theory. Basically, additive color theory talks about adding the three primary colors of light, red, blue, and green. And when you add these three together, if your eye receives equal input from all three types of cone cells firing equally, then what we get is white light. And this is why it's called the additive theory, because we're adding these three wavelengths, red, green, blue, to produce white. And the primary colors are red, green, and blue. And you can see this in effect when you look at projection monitors, TV screens, computer screens. If you look at them with a microscope, you can see how, or a magnifying glass, sorry, you can see how they're all made up of pixels or tiny little dots of lights that are red, green, or blue, and they're able to produce every color possible by mixing red, green, and blue, or adding red, green, and blue, or red and green, green and blue, a little bit of green. All the different combinations that you could get will produce all the different colors. We also talked about how the secondary colors of the additive theory were, if I take red plus green, and then we can do red plus blue, and the other combination would be green and blue. And if we add these equally, we get what's called the secondary colors of the additive theory. And we're going to use those as the sort of jumping off point for where we're headed next. Let's see. Here's the magenta one, which you get from red and blue, so we get the color magenta. This is the secondary additive color. Green and red produces yellow. This is the hardest one to understand, but it is true. At least the magenta looks like a blue and red mix, and the cyan looks like a blue-green mix, but yellow doesn't look like a mix of red and green at all. So it's kind of an enigma, but nonetheless, that's what it is. And then we would need cyan. Here's an interesting, reasonably good cyan color. So these are the secondary colors of the additive theory. What's interesting, though, is we're going to now talk about the subtractive theory, which is kind of the same thing, a little bit in reverse. But this one will seem a little more familiar to you, because it'll blend more with what you were taught in kindergarten. The primary colors of subtractive theory are the secondary colors of the additive theory. So our primary colors are yellow, magenta, and cyan. All right? Now, because it's a bit of a pain to shift and get those colors, they're not readily available. Give me a second, I'll see if I can get them to come up on my little color pad so I can do that easier. Okay, I think I've got it worked out so we can use those colors. So if I click here, I can get magenta. And I can also grab cyan fairly easily. And I can grab yellow. All right. These are very close to the colors that you find in the ink. Well, they are the colors you find in the ink on your printer. So when we start thinking about pigments, the word pigments means things that color things, like inks and paints and stuff like that. And subtractive theory lends itself more to understanding why things are certain colors. Now, when you were a little kid, you probably learned that the primary colors for coloring were red, blue, and yellow, right? And you probably learned things like, well, if you mix blue and yellow, you get green. And you might have learned that mixing red and blue makes purple. Well, that's actually not quite accurate. The problem is there are many shades of red, and magenta could be considered to be a shade of red. And of course, there's many shades of blue, and cyan could be considered a shade of blue. Subtractive theory tells us that, what I'm going to do is put these in brackets, because they're not really the real ones. Subtractive theory tells us that if we add our three primary colors, magenta, cyan, and yellow, what we're supposed to get is, because of subtractive theory, we're supposed to get black, which is no color at all. Now, when I was a kid, and they told me about red, blue, and yellow, I remember going to the paint station in grade kindergarten and grade 1, and mixing red, blue, and yellow together, hoping to get black. But it never, ever worked. I always got this dull, crappy brown color. And it didn't matter how much red, or how much blue, or how much yellow I used. No matter what I tried, I could never get red, blue, and yellow to make black. And that's because they don't. Not in the sense that we think of those colors. In order to get black, you have to use the magenta shade of red, the cyan shade of blue, and the yellow color with it. If you mix those three colors, you will get black, and your printer does it all the time. If you run out of colored ink on your printer, if you run out of black ink and you need to print your essay out, your printer will simply mix those three colors together, and it will make black ink out of the colored ink. And it'll make beautiful black ink that looks the same as it would have if you'd used the actual black ink cartridge. So the subtractive theory works if you think of the primary colors as these three, magenta, cyan, and yellow. But they are shades of red and blue, aren't they? So you can see why in kindergarten they would simplify it. Little kids can't spell magenta, but they could spell red. So we simplified that. So that explains that part of it. Now, what's interesting is how they work. So let's take an object that is magenta in color. So I'll take my magenta box here, and I'll draw a little box, magenta. What does that mean? Well, in order to see magenta, remember from additive theory, that's a mixture of red and blue. So when white light shines upon this object, we have red light hitting it, green light hitting it, and blue light. Remember, the three colors together are white. So if we shine normal white sunlight is pretty much white, then what should happen is the blue should reflect off the object to our eye, and so should the red. But what happens to the green? Remember, the green reacts differently. When it interacts with the molecules of this particular pigment, it turns into heat, or we say it gets absorbed. We can't see it, which means it's taken out of the equation. So what we say is that magenta, whoops, that's purple. Magenta subtracts, I lost my colors. Magenta subtracts green. Okay, what's happening now? Magenta subtracts green. Give me a second here to fix what's happening here. My pen. I'm getting a weird line. You have to give me 1 second to straighten this up. Okay, sorry about that. I got it figured out. Sometimes technology likes to fool us. So I've got my magenta color. We were saying that magenta subtracts green. It absorbs green, takes it out of the equation. So an object that is magenta in color, or a paint or a pigment that is magenta in color, will remove green from your eye. In other words, it will prevent the green from reflecting to your eye. Okay, let's do the same kind of a picture with the yellow object. I'll just do that one over here. Here's a yellow object, and again we have our red, green, and blue light that comes in. White light is all three. This time, the green will reflect to your eye, and the red will reflect to your eye, but the blue light will be absorbed or turned into heat, which means that yellow effectively removes blue. It subtracts blue from the white light that's shining on the object. So a yellow object subtracts blue. So it's kind of like all we're doing is instead of looking from the point of view of what is reflected, we're looking at the point of view of what is absorbed. Okay? Subtracts blue there. And then we have one more color, which is cyan. Grab that here. So here's a cyan object with a green color. And if we have white light, which is red, and green and blue all together, what happens here is the blue is reflected to the eye, the green is reflected to the eye, but the red light is absorbed or turned into heat. So we say that cyan subtracts or absorbs red. So you can see how it's kind of the backwards of the additive theory, where we were talking about these primary colors, green, blue, and red, mixing and adding together to produce the secondary magenta, yellow, and cyan. And now we're looking at the point of view how magenta, yellow, and cyan remove one of the three primary colors and produce the colors, the primary colors of subtractive theory. So cyan, yellow, and magenta. Okay, so it's really that straightforward. Let's just imagine what would happen if you mixed paints together. All right, so what if you took some, let's do the old, the blue plus yellow makes green. Remember that from kindergarten? But we know now that it's not technically blue, it's cyan. So let's experiment with cyan. And then if you mix that with yellow, you're supposed to get green. So we're mixing pigments or paints. And now let's look at it from the point of view of what each of them does. Well, remember what cyan does. It subtracts red. So it takes red out of the equation. And yellow subtracts blue. So of course, if you're shining an object that is a mixture of cyan and yellow, if you have three colors, I'll have to draw the object in green because that's what color it's going to be, right? So what this really is it's a mixture, and I'll write this down so we can see it. The reason it's green is because it's a mixture of cyan and a mixture of yellow. Okay? So that's what's actually doing. Yellow and cyan paint mixed together produce this object. Well, when you shine light on this object, the cyan is subtracting red, which means that the red is being turned into heat by the cyan pigment, but the yellow is subtracting blue, which means blue is being turned into heat by the yellow pigment, which leaves the green left alone to shine and reflect to the eye. So cyan plus yellow paint, or ink, will make a beautiful green color because of what they subtract. So that's the subtractive color theory, and that's a little bit more in line with the way that you learned it in kindergarten. And really that's all we need to worry about for now.